Hydrogen bonding? Yes. We do have a nitrogen. We have 9 hydrogens in there, but none of the 9 hydrogens are directly attached to nitrogen. No hydrogen bonding. Okay. So the next case, dimethyl ether. Okay. We have CH. Hydrogen bonding. You have oxygen. You got 6 hydrogens in there, but none of the 6 hydrogen is directly attached to the oxygen. No hydrogen bonding. Acetic acid, the last one. And you draw the Lewis structure. Now you see the importance of the Lewis structure. It shows you the electron distribution as well as how atoms are connected to one another. So acetic acid, well, there are 2 oxygens in there. One oxygen has a hydrogen directly attached to it. Hydrogen bound. So this is what you need to look for when we ask you this kind of question. What types of molecules can hydrogen bond? You're looking for nitrogen, you're looking for fluorine, and you're looking for oxygen. If a molecule has one of those 3 atoms there, you also need to look whether or not there is a hydrogen directly attached to one of those 3 atoms there. If there is at least one hydrogen attached to it, yes, hydrogen bonding. Otherwise, no. Okay, so this is the kind of intermolecular forces that are involved in polar molecules. And we want to switch gears to another type of molecule, nonpolar molecules there. Now in nonpolar molecules, we have what we call the dipole and induced dipole interaction. Okay. Now we also have what we call the induced dipole interaction. What are these terms? How do we define these terms there? Now let's take a look at what happens in nonpolar molecules versus when you have a nonpolar molecule versus polar molecule. Well, let's take a look at what happens there. Now, oxygen we know is a nonpolar molecule. Water is a polar molecule. However, oxygen can dissolve in water, which we should be thankful. Otherwise, there would be no such thing as aquatic life, as we know of. Oxygen is essential for the life, different types of lives exist in water there. But nonpolar molecule oxygen can dissolve in water. Now, how do we explain that? Well, the thing here is that water has a permanent dipole. One end of water molecule has positive charge, the other end has negative charge. Now, oxygen molecule is nonpolar. Now, in this case, if you have oxygen atom and if you have a water molecule there, if they get close enough to one another, temporarily, this negative end of water molecule can attract the positive end, the positive particles within the oxygen molecule, okay, and distorting the electron cloud, making the other side of the oxygen molecule slightly negative. Okay, so this negative end in water molecule attracting the positive charges within the oxygen atom, giving you a temporary distortion of electron cloud. Now, this particular interaction is the result of the presence of the dipole of the polar molecule here. So we call it induced dipole. This dipole moment in the nonpolar molecule will not exist unless you have a polar molecule near. So in this case, we call it induced dipole. So this is dipole-induced dipole interaction. That's how nonpolar molecules interact with polar molecules. Okay. Now in this case, we can understand the solubility of different types of gases. Most of the gases there in the elemental gases, like hydrogen gas, chlorine gas, and nitrogen gas, and oxygen gas. If they dissolve in water and there's no chemical reaction happening there, then a certain amount of gas will be able to dissolve in there. As the molar mass increases, the solubility increases. So what we saw here, based on the experimental data, for hydrogen gas in 2 grams per mole, okay, every 100 grams of water at 20 degrees Celsius will dissolve 0.00016 grams of hydrogen gas. Going to nitrogen, going from 2 grams per mole to 28 grams per mole, you see an increase in the solubility, and almost a little bit more than tenfold. Because you have 3 zeros there, and you only have 2 zeros in here. Now, if you go from 28 to 32, nitrogen gas to oxygen gas there, and you see a little bit more than solubility increase a little bit more than double. Okay, 0.0019 versus 0.00434. What can we conclude based on this particular data table there? And we say that the degree to which the electron cloud of an atom or molecule can be distorted is measured by polarizability. Among the larger the molecule, the higher, the more easily it is polarized. So this indicates that as the electrons in the molecule become more loosely held surrounding the positively charged center, then the greater degree of polarizability are exhibited in the molecule there. And this explains within why when you have an increase in molar mass there, you see an increase in solubility, because it's getting easier and easier for water molecule to polarize the larger molecules there. So size actually matters here, and it actually makes a difference in terms of solubility. And oxygen can actually dissolve in an appreciable amount in water to support aquatic life. Okay, so this also has something to do with intermolecular forces there, and this involves the intermolecular forces between a polar molecule and a nonpolar molecule. Now, the forces involving the induced dipole there is that even when you have nonpolar molecules, like iodine, if you can single out one iodine molecule will be nonpolar. If you separate them far apart from one another, there will be no interaction. However, iodine is a solid. The particles are packed very closely to one another. So if you put them close enough to one another in the solid form, there will be attractions. The positive charge in one molecule will be attracted to the negative charge of the other. So as long as the two nonpolar molecules are close enough to one another, you will result in what we call a momentary attraction there, resulting in an induced dipole. Both dipole moments in both molecules are induced by each other. So this is what we call the induced dipole. We also give it the name London dispersion force. Now, London dispersion force exists in all types of molecules, regardless of polarity. But in polar molecules, London dispersion force is so weak, we normally do not consider them, but they do exist. So that's something that we do need you to remember. So again, London dispersion force exists among all molecules, polar or nonpolar. And London dispersion forces are a function of molecular polarizability. And molecular polarizability is a function of size. So the bigger the molecule, the easier they are being polarized, and this results in a higher amount of attraction there. So the polarizability is measured of a molecule is measured by how easy it is within an electron cloud can be distorted. And so the bigger the molecule, the greater the polarizability. The greater the surface area available for contact, the greater the dispersion force. Okay, so this is something that we want you to remember. And again, London dispersion force therefore increases as the molar mass increases, or molecular weight. I should change that to molar mass there. Okay, so as the molecule is getting bigger and bigger, it's easier and easier to distort their electron cloud, making it experiencing a higher amount of London dispersion force. Now,